with Z is stuck at 1. And in that case, what will happen? What would happen to Z? Well, this is always 1, and since this is an OR gate, so output is, well, it's always 1, right? And if Z is stuck at 1, that implies, well, it implies that Z is 1. So notice here, this fault and this fault, they have the same effect. And sometimes that will happen. So some faults could have the same effect for all possible situations. And later on, we are going to term them as equivalent faults. Okay, now let's, so notice, according to the model, you can have a defect at a gate input, a gate output, or a primary input. C here is, what is it? Is it a gate input or gate output? I guess it's both, but so we can consider it either. Now let us continue this example and let us ask this question. Find a test for x2 stuck at 1. So basically this is stuck at 1 and you have to find a test for it. And answer is, okay, so right now don't ask how I got the answer, but you can check if the answer is correct. And later on, we are going to look at the problem of test generation. So we are going to see how we find the answer, but let's just check out the answer and let's see if that is correct. So the vector x1, x2, x3 equal to 0, 0, 1. And now in this case, output is going to be, now let's assume that this fault is not there, then what will be the output? So we are applying 0, 0, 1, and there's no fault in there. And obviously this is 0, and this is 0, and this is 0. So it is 0 normally. Now we have to figure that out here. And what if the fault is there? If line x2 happens to be stuck at 1, this is a usual abbreviation. We'll say stuck at 1. So if line 2 is stuck at 1, then even though we are applying a 0 there, basically the line will behave as if it is always 1. And so here we have a 1, and here we have a 1. So here we are going to have a 1. Now this 1 here, of course, doesn't matter. So this 0 still stays 0. And because we have a 1 here, so this is a 1. So it is equal to 1 when the fault is present. So the conclusion is that this is a test. Thus, 0, 0, 1 is a test for x2 stuck at 1. Now notice here that we are not claiming that if you apply 0, 0, 1, and if you find that the output is faulty, then it is this particular fault. We are not claiming that. It could be because of some other fault, we don't know. But what we are claiming is that if this fault is there, then this test will detect for that fault. Now, as we are going to see later, it is quite common that a single test will actually test for several faults. Okay, now let us come to the single fault assumption. So we were discussing that last time, and some of you thought that it is not a good assumption, which is true in some cases, but in some cases it is a good assumption. And let me tell you why. So basically the assumption is that only one fault is present at a time. That is the assumption. And the advantage, of course, is that it significantly reduces the complexity. You consider one fault at a time, and so you ask the question, is this fault going to be tested? Is this fault going to be tested? Is this going to be tested? And so on. It is good for fault detection. But not good for fault location. So if you assume, if your objective is to see if something is good or bad, if you want to simply detect a fault and say that whether this has a fault or not, then this is a good assumption. Now it is possible that you can have two faults at the same time, and somehow the second fault makes it impossible for the first fault to be found. In that case, this will turn out to be a bad assumption. If one fault can mask the effect of another fault, that can happen, however, it's relatively unlikely. So unless a fault can mask the effect of another fault, somehow you have two faults happening and they cancel each other out. Probably not very common. So should be good for fault detection. However, for fault location, this is not a good assumption, because if you have two faults at the same time or three faults, they can have some output response, and the output response may not tell you whether you have this fault or that fault, or perhaps a combination of faults. So it is not good for fault location. But for fault detection, it is a good. And another thing to note is that now sometimes we talk about multiple faults. So basically, whenever we will talk about a multiple fault, that means simultaneous presence of multiple faults. I'm repeating the term, several single faults. So if you have a fault here and a fault here, and if they have presented at the same time, you will refer to that as a multiple fault. Now, problem of multiple faults is that how many multiple faults you can have in the circuit. Let us say if you have a circuit with key lines, just like here in that circuit we had a number of independent lines. So now at a particular line, so let's say here is a line. So here this could be stuck at 0, or it could be stuck at 1, or it could be normal, right? So any node could be any one of these three. So with so you have basically three states per line. And if you have k, then you have a total of 3 raised to k different situations. And of course, one of them is a good, so faulty combinations. So remember that you have k here in the exponent. Okay. How much do you think this would be if k is equal to, let's say, 1,000? A circuit has 1,000 nodes, which is not particularly big for these days. If you have a microprocessor, you have probably millions of gates there. So let's say if you have 1,000, how much is 3 raised to 1,000? Okay, anyone has a calculator? Okay, so if you will try a calculator, you are going to come up to a number which is 1.3 multiplied by 10 raised to 47. Oh, I'm sorry. 1.3 multiplied by 10 raised to 477. So basically an enormous number of combinations. So if you want to consider all possible multiple faults, all possible combinations, that is going to be an enormous number of possible combinations to consider. So one reason to go with the single fault model is that if you don't, things could become very hard. Now there are some researchers who have thought about multiple faults. So they have thought about multiple faults and some regular structures where somehow things could be generalized. But in general, people don't talk that much about multiple faults unless you are talking about fault location, which is a harder problem. So usually we will assume a single fault. Okay, so this is about stuck at 0, stuck at 1 faults. And now let us look at another fault which is also, we can characterize at the gate level. Let's talk about the delay faults. Now, as you know, everything in a digital circuit is a sequential circuit. That means signals start from somewhere and they go to some place, and they need to arrive, all the transitions, at the destination latches within the specified period of time, perhaps a clock period, and then the values are sampled there. So if they are not stable within the given time, the value sampled is going to be incorrect. Now you can have some defects. You can have some defects which don't cause a logical problem. Your circuit will still work, but your gates will respond slowly. When a circuit chip is manufactured, they have some estimate of how much the delays are going to be, and using some modeling tools they can estimate. But the manufacturing process cannot be exactly controlled. So delays are never going to be exactly what they expect, but they have kind of a statistical expectation. So there will be some that would be faster than what they expect, and there would be some that would be slower than what they expect. And some defects could cause some gates to have too much delay. So in other words, you have excessive propagation delay.